Okay, so layer arrangement is important as well. So just as some quick examples, in the first stack up, the signal layers are adjacent to each other, and that is definitely prone to crosstalk and EMI. And the ground plane is further away from the signal layers. In the second example, the clearance between the power and ground plane is very high, and there's a split in the power plane. So the third stack up is really, let's say, the best, would perform the best. So place signal and reference planes as close as possible together. Do not place signal layers next to each other. Avoid split reference planes. Couple the power planes with ground planes for low inductance distribution. These are some of the basics. So why do you need to place signal layers close to ground planes? So just as a quick bread and butter, a transmission line consists of a trace and its return path, and the image shows a strip line configuration of a transmission line with ground layers on top and bottom. When the energy is applied to the transmission line, the EM field travels through the dielectric space and flows to the neighboring copper if there's a low impedance path. So if this field is not regulated, it leads to signal integrity issues. So have less dielectric spacing between the ground and signal planes to reduce the impedance of your signal path, and an unbroken ground plane per microstrip helps contain the EM field. So here's another example how adjacent signal layers create EMI issues. So when the EM field from layer 1 passes through layer 2 to reach the reference plane in layer 3, it gets coupled with layer 2 EM field. This coupling can induce a common mode current, which can lead to EMI. Redesigning the stack up is the best way to avoid this. If you don't want to change the stack up, route traces are orthogonally between the two layers, and add copper 4 and ground trace on layer 1 to reduce the severity. So routing signals over a split plane will also cause signal integrity issues. If you'd like to route a signal on the power plane, make sure the trace is not passing through the split, and that's shown in the image below. So in high-speed designs, the splits can generate spikes that lead to ground bounce and undesired voltage drops. So some advantages of placing power planes next to the ground plane. If the power and the ground plane are close to each other, let's say 8 mils, it will act as a high-frequency capacitor. So it creates the low impedance distribution network for power and ground connections, and it helps in reducing EMI when signal is transitioning from the layers. And so other power plane considerations: place 2 adjacent power planes as far as possible to avoid unwanted coupling. Add a reference plane near the power plane to give a low inductance path, and do not route the signal layer between the ground and power as it creates coupling issues. So here are some best practices for a layer transition through vias. So if you minimize the size and the number of vias, this will reduce the risk of impedance mismatch. You can also employ back drilling to avoid the stub reflection. And back drilling should be a widely used technique if it can eliminate additional laminations. So if your via transitions between 2 ground planes, use ground via with signal via as shown in the image. If your via transitions between power and ground planes, place a decoupling capacitor at the transition point as shown here.